I was staring at the engineering report when the world changed forever, though I didn't realize it at the time. December 18th, 2025, Samsung SDI's internal documentation had just leaked across my desk. Technical specifications for their solid-state battery production line that would enter mass manufacturing within 18 months. The media was calling it a breakthrough in electric vehicle technology, celebrating 9-minute charging times and 900-mile range capabilities, but they were missing the single most dangerous detail buried in Appendix C of the materials specification. The document was 247 pages of highly technical Korean engineering data, most of it focused on manufacturing processes and quality control parameters that would interest only battery specialists. Charts showing cathode optimization algorithms, graphs demonstrating electrolyte stability under thermal stress, endless tables of charging cycle performance data. But buried on page 184, in a subsection titled Anode Interface Materials, was a specification that would reshape global commodity markets within 2 years. While analysts cheered about lithium and cobalt demand projections, I found myself staring at a line item that made my hands shake. Silver carbon nanocomposite anode coating, minimum loading density 8.7 grams per kilogram of active material. That might sound like technical gibberish to most people, but I understood what it meant for the global commodities market. Samsung had just weaponized chemistry itself. They had solved battery technology's most persistent problem by creating an unprecedented demand shock for one of Earth's scarcest metals. The implications were staggering, and I realized that most of the financial world had no idea what was about to hit them. For 3 decades, every lithium-ion battery on Earth had been fighting the same invisible enemy: dendrites, microscopic needle-like crystals that grow inside batteries during charging cycles like metallic cancer cells. These whisker-thin formations start at the anode surface and grow toward the cathode, piercing through the delicate polymer separators that keep the battery's positive and negative sides from touching. When dendrites complete that circuit, batteries don't just fail. They become incendiary devices capable of reaching temperatures exceeding 1,200 degrees Fahrenheit. The faster you charge a battery, the more aggressively dendrites form, which explains why electric vehicles take 45 minutes to charge and why Samsung Galaxy Note 7 phones were banned from commercial aircraft. Every battery engineer knew that solving dendrite formation was the holy grail that would unlock instant charging and eliminate thermal runaway risks. Hundreds of companies had spent billions pursuing various solutions: graphite additives, silicon nanowires, polymer coatings, ceramic separators. All had failed or created new problems worse than dendrites themselves. But Samsung's researchers had discovered something that changed everything. They found that one specific element, when applied as a nanometer-thick coating on lithium anodes, completely eliminated dendrite formation while maintaining perfect electrical conductivity. The element created a uniform surface that allowed lithium ions to deposit evenly during charging, preventing the irregular crystalline structures that became dendrites. That element was silver. I immediately called my contact at Heraeus Precious Metals in Hanau, Germany, because I needed to understand the supply mathematics that Samsung's procurement team was undoubtedly calculating in their Seoul headquarters. Wolfgang had been tracking precious metals markets for 23 years and understood the industrial demand patterns better than anyone in Europe. "How much refined silver can the global market produce annually?" I asked, though I already suspected the answer would terrify me. "About 830 million ounces from mining, maybe 180 million from recycling," he replied after a pause. "Most recycling comes from photography and electronics, but the yields are dropping as technology miniaturizes. Why are you asking? Are you seeing unusual buying patterns?" I didn't answer his question directly, but instead started calculating while he was still on the line. Global automotive production averages 90 million vehicles annually. If Samsung's solid-state technology captured even 30% market share by 2028, a conservative estimate given their technical advantages, we were looking at 27 million vehicles requiring silver carbon anodes. At the loading densities specified in their engineering documents, that represented approximately 50 million ounces of new annual silver demand, equivalent to the entire mining output of Mexico, the world's largest producer. But my conservative estimate was quickly proving naive as I dove deeper into Samsung's technical specifications. I discovered that they weren't just coating anodes lightly with silver nanoparticles. They were engineering comprehensive thermal management systems that required silver tin oxide contacts throughout the entire battery architecture. High-voltage switching systems, emergency disconnect mechanisms, thermal sensors, and current distribution networks all demanded precious metal components that could survive the electrical stresses of 9-minute charging without degrading. Moreover, Samsung was implementing redundant safety systems that multiplied silver requirements exponentially. Each battery pack contained not one, but three independent monitoring circuits, each requiring silver contacts for reliability. The battery management system included fail-safe mechanisms that could isolate individual cells during thermal events, and every isolation switch needed silver alloy contacts to function under extreme conditions. When I calculated the total silver loading per vehicle, including all safety systems and backup circuits, the number reached nearly 200 grams, more than 6 ounces per car. The automotive industry was walking into a materials trap without realizing it. Tesla, Ford, General Motors, Toyota, and Volkswagen were all rushing to license Samsung's technology or develop competing solid-state systems, but none of them had done the mineral resource analysis. They were designing a future that required more silver than physically existed in available inventories, and their engineering teams were blissfully unaware of the commodity crisis they were about to trigger. I started tracking industrial buying patterns through my contacts in the London bullion market, and the data painted an increasingly disturbing picture. Samsung Electronics had quietly contracted with three separate mining companies for multi-year silver supply agreements at fixed prices, effectively removing 15 million ounces annually from the open market before their production lines even started operating. The contracts were structured as tolling agreements, where Samsung would finance mine expansions in exchange for guaranteed delivery at predetermined prices, insulating them from market volatility while creating artificial scarcity for everyone else. LG Chem was negotiating similar deals in Peru and Bolivia, approaching smaller miners with offers that included upfront capital investments and equipment financing. Chinese battery manufacturers, BYD, CATL, and Goshen High-Tech were moving even more aggressively, sending teams to Mexico and Argentina to negotiate exclusive offtake agreements that would lock up silver supplies for the next decade. The smart money had already figured out what the financial press was missing. This wasn't just another incremental improvement in battery chemistry, it was a fundamental shift that would transform silver from a precious metal into a strategic industrial commodity as essential as lithium or rare earth elements. By February 2026, I was watching the first cracks appear in the global silver supply chain through indicators that most market observers missed entirely. Silver futures prices had begun climbing from their traditional $25-30 range toward $40, but the real action was happening in the physical market, where industrial users competed for immediate delivery. Premium spreads between paper contracts and actual metal were widening to levels I hadn't seen since the 2008 financial crisis, when liquidity constraints forced banks to pay massive premiums for physical assets. The London Bullion Market Association reported inventory drawdowns that accelerated throughout the winter as industrial users shifted from just-in-time purchasing to strategic stockpiling. Companies that had historically bought silver monthly were now contracting for yearly supplies, removing material from circulation and creating artificial scarcity that rippled through every sector of the market. Samsung's pilot production line in Cheonan was consuming approximately 2,000 ounces of silver daily just for prototype batteries and testing protocols, and that was before any automotive partner had committed to volume production. Industry sources suggested that full-scale manufacturing would require a 100-fold increase in silver consumption, creating demand that dwarfed traditional industrial applications like solar panels, electronics, and telecommunications infrastructure. The mining executives I spoke with were uniformly pessimistic about responding to increased demand through production expansion, and their explanations revealed the fundamental structural problem that Samsung had unwittingly created. Silver is mostly a byproduct of lead and zinc mining, explained Carlos Mendez, CEO of a major Mexican operation that produced 12 million ounces annually. Even if silver prices doubled or tripled, we can't just decide to produce more silver. We produce what comes out of the ground with the base metals that drive our economics. This byproduct reality created an economic nightmare that Samsung's financial planners were apparently just beginning to understand. Unlike copper or aluminum, where higher prices incentivize expanded mining operations and new project development, silver supply remained hostage to demand for entirely different metals. If the global economy slowed and reduced zinc consumption for galvanizing and construction applications, silver production would actually decrease even as battery manufacturers desperately needed more material. The geological constraint was even worse than the economic dependency. Virtually every major silver deposit discovered in the past 50 years had been found accidentally while exploring for copper, gold, or base metals. Primary silver mines, operations specifically designed to extract silver as their main product, were rare, difficult to finance, and typically located in geopolitically unstable regions. The largest primary silver mine in the world, Mexico's Fresnillo operation, produced only 50 million ounces annually and was already operating near maximum capacity. I realized that Samsung had inadvertently triggered a resource competition that extended far beyond their Korean headquarters into every corner of the global economy. Chinese solar panel manufacturers were already consuming 150 million ounces annually for photovoltaic applications, and they weren't going to reduce usage just because Samsung needed silver for batteries. Electronics companies required silver for smartphones, computers, telecommunications infrastructure, and the explosion of Internet of Things devices that were embedding silver circuits in everything from refrigerators to traffic lights. Investment demand from individuals and institutions added another 250 million ounces of annual consumption as sovereign wealth funds, pension plans, and private investors sought protection against currency debasement and inflation. Central banks in emerging markets were increasing their silver reserves as part of monetary diversification strategies, removing millions of ounces from commercial markets permanently. Adding 50 to 100 million ounces of automotive demand to an already tight market meant something fundamental had to give. Either prices would rise high enough to destroy marginal demand applications, forcing manufacturers to redesign products around different materials, or supply shortages would create allocation systems that prioritized certain industries over others. But Samsung couldn't simply substitute away from silver without abandoning the fundamental chemistry that made their breakthrough possible. Silver's unique properties made it irreplaceable for their specific application. It possessed the highest electrical conductivity of any metal, crucial for handling the high current densities of rapid charging. Its thermal properties allowed heat dissipation without creating hot spots that could trigger thermal runaway. Most importantly, silver formed conductive oxides when exposed to air, meaning that even if the surface oxidized, electrical conductivity remained intact, a critical safety feature when dealing with high-energy battery systems. I watched the first signs of panic buying emerge in March 2026, when Tesla's procurement team realized they had underestimated silver requirements for their next-generation 4680 battery cells by a factor of 3. Internal documents that leaked through supplier channels suggested they needed to secure 8 million ounces immediately to avoid production delays at their Austin Gigafactory, but the physical market couldn't absorb that kind of sudden demand without triggering price spikes that would cascade through every silver-dependent industry. Tesla's purchasing agents contacted every major bullion dealer simultaneously, offering massive premiums for immediate delivery. This pushed physical premiums to levels not seen since 1980, draining Western inventories into Asian manufacturing centers. Samsung's stock price soared on expectations of market dominance, but materials costs were becoming problematic. Silver budgeted at $30 per ounce was now trading above $50, adding hundreds to each battery pack's cost. By summer 2026, the situation had evolved from a supply challenge into a full-blown geopolitical crisis that threatened international trade relationships and forced governments to choose between industrial policy objectives and free market principles. Mexico, which produced 25% of global silver through operations in Zacatecas, Chihuahua, and Durango states, imposed export restrictions to ensure domestic battery manufacturing facilities had adequate materials for proposed joint ventures with American and European automakers. The Mexican government's decision was driven by recognition that silver had become a strategic resource comparable to lithium or rare earths. Rather than allowing their national mineral wealth to flow freely to foreign manufacturers, they wanted to capture more value-added production domestically. President López Obrador announced plans for a state-owned battery manufacturing facility that would process Mexican silver into finished battery components, keeping both the resource and the manufacturing jobs within national borders. China responded by implementing even more restrictive policies, completely banning silver ore exports and requiring all domestically mined silver to be refined within Chinese territory. This forced international companies to either partner with Chinese refiners, sharing technology and accepting Chinese oversight, or source silver from more expensive suppliers in politically stable but geologically limited regions. The United States government found itself caught between competing policy objectives. The Biden administration had committed to rapid electrification of transportation as part of climate change mitigation strategies, But achieving those goals required secure access to battery materials that were increasingly controlled by strategic competitors. In August 2026, the White House invoked the Defense Production Act, classifying silver as a critical strategic material and prioritizing military applications over commercial battery production. This classification triggered a cascade of unintended consequences throughout American industry. Defense contractors working on missile guidance systems, radar arrays, and communications equipment received priority allocation for silver supplies, but civilian manufacturers found themselves competing for increasingly expensive material in spot markets. Solar panel installations slowed dramatically as silver costs made projects economically unviable, ironically undermining renewable energy deployment in the name of electric vehicle production. European Union trade officials were simultaneously negotiating emergency mineral agreements with Canada and Australia, trying to secure reliable supply chains that bypass the increasingly hostile resource nationalism emerging from major producing countries. But even traditionally stable suppliers were reconsidering their export policies as domestic demand increased and governments recognized the strategic importance of battery materials. The price discovery mechanism was completely breaking down by late 2026, creating a bifurcated market that confused traditional analysis and made hedging nearly impossible. Spot silver prices reported by exchanges bore little resemblance to the premiums that industrial users were actually paying for immediate delivery. The divergence reached extremes where paper silver traded at $55 while Samsung was reportedly paying $75, $80 per ounce for guaranteed supply chains that bypassed volatile spot markets entirely. This price divergence created arbitrage opportunities that drained physical inventories from Western vaults into Asian manufacturing centers, fundamentally altering global silver flows in ways that would persist for years. European refineries were shipping silver directly to Korean and Chinese battery plants, rather than selling into traditional distribution networks, leaving coin dealers and small manufacturers unable to source adequate supplies at any price. The automotive industry's electrification timeline was beginning to fracture under materials constraints that nobody had anticipated during the initial planning phases. Ford delayed their solid-state battery rollout by 18 months, citing supply chain complexities in press releases, while privately acknowledging that silver costs had made their business case impossible. General Motors announced they were exploring alternative battery chemistries that used less silver, though their technical teams privately admitted that performance would be compromised and safety margins reduced. Stellantis took a different approach, announcing a partnership with First Majestic Silver to finance mine expansion in Mexico in exchange for guaranteed silver supplies. The $500 million investment would increase production by 8 million ounces annually, but wouldn't come online until 2029. Too late to help with immediate production needs but potentially valuable for long-term competitive positioning. Samsung found itself in the peculiar position of having solved battery technology's most persistent problem, while simultaneously creating an unsolvable materials crisis that threatened to constrain their own success. Their engineering triumph was bounded by geological reality. There simply wasn't enough silver available to electrify the global vehicle fleet using their breakthrough chemistry. Samsung recognized that controlling raw materials had become as critical as controlling technology. They began vertical integration through direct mining investments, announcing joint ventures in Idaho, Nevada, and British Columbia to secure long-term supplies at fixed prices. I watched the final collapse of traditional silver market dynamics in early 2027, when speculative traders were completely overwhelmed by industrial demand that operated according to different economic rules than financial markets had ever seen. Hedge funds buying silver futures for profit margins were competing against battery manufacturers buying silver for corporate survival, and survival always wins that competition. The transformation was complete. Silver evolved from a precious metal traded by investors into a strategic industrial commodity controlled by governments and corporations. Countries without domestic silver supplies found themselves dependent on others for battery materials, creating new economic leverage and potential conflicts. Samsung's solid-state battery technology achieved everything their engineers had promised, eliminating dendrite formation, enabling 9-minute charging, and providing unprecedented safety margins. But the silver they consumed to achieve this breakthrough was locked away in battery packs for the next 15 years, removed from circulation and unavailable for other applications that had historically depended on silver's unique properties. The broader implications were still unfolding. Traditional silver applications, jewelry, electronics, were being priced out by automotive demand. Investment patterns shifted as individuals found themselves competing against industrial giants with unlimited capital. As I write this assessment, Samsung's batteries power millions of vehicles with unprecedented performance. Tesla's Model S charges in 8 minutes. BMW's iX travels 950 miles per charge. Mercedes eliminated thermal management entirely, relying on silver's heat dissipation. But the silver consumed is locked away for 15 years, unavailable for other applications. The automotive industry consumed 127 million ounces in 2027, establishing new price floors for the 2030s. The true cost of solving the dendrite problem wasn't measured in research and development expenses or manufacturing investments. It was measured in the permanent restructuring of global materials flows, the emergence of resource nationalism among producing countries, and the recognition that Earth's mineral constraints can limit even the most brilliant technological solutions. Samsung had successfully dropped their silver bomb, eliminating one of battery technology's most persistent challenges while creating unprecedented demand for one of Earth's scarcest metals. The explosion reshaped global commodity markets, altered international trade relationships, and forced recognition that technological progress remains bounded by geological reality. The question that kept me awake at night wasn't whether Samsung's technology would succeed. It already had. The question was whether global silver supplies could sustain the electrification revolution that Samsung had made possible, and what would happen to the millions of other applications that depended on silver's unique properties when automotive demand consumed available supplies. History would remember Samsung's solid-state battery breakthrough as the moment when technological innovation collided with planetary resource limits. Whether that collision produced sustainable progress or merely delayed an inevitable reckoning remained to be seen.